Okay, so today, what we're going to do today is we're going to take a look at something called heating curves. Up to this point, we've figured out how much energy is involved in transferring heat energy from one substance to another. Like we took a piece of metal and we put it in some water, and we looked for the temperature changes, and we were able to measure the delta E, the change in energy. And that all was fine. That all worked great, assuming that we didn't have a change of phase. That is to say, we didn't go from liquid water to solid or to gas. Because when that happens, well, something different is going on there. We're having molecules being pulled apart from each other. And so we have to take that into account. So today what we're going to do is we're going to do something called a heating curve. And we're going to take a look at what happens when we change states of matter. And then we'll also touch upon something called heat capacity, again, and how we figure out how much energy is in our food. How do they come up with those labels, like how many calories are in a gummy bear? All right, so now to get us started, we're going to make a graph. And so in your notes, I'm going to encourage you to follow along with us and write this graph in your notes. And we're going to put some labels in there. So give yourself a little bit of space, make it fairly large so we can put some notes in here. And we're going to start out down here on the bottom, and we'll say down here, heat added. And then over here, we'll have our temperature. So degrees Celsius and heat added, like this, like that. And so here's 0 degrees, and okay, well, that looks pretty. All right. And the question here that we have before us, it says we can track changes in temperature and physical states as water goes from snow at a negative 18 degrees all the way up into boiling water. So negative 18 degrees, well, that's going to be down here somewhere. So like negative 18 degrees is down here, negative 18 degrees Celsius. And that water, as we heat it up to 0, we're going to add some energy to it. So we're going to add some energy to that ice until we get it to 0 degrees. And once it's at 0 degrees, we would melt it. And so we would add heat energy, and that ice there would melt as we're going from here to here. But notice the temperature doesn't change. So when you have like a glass with water and there's ice in there and the ice is melting, the temperature doesn't change. It's still at 0 degrees. Now once all that ice is melted and we're still at 0 degrees, we can add more heat energy to it, and we can boil it. And so when we boil it, we bring it up to 100 degrees. Bring it up to 100 degrees. And now it's boiling. We have boiling water here. Up here, okay, so water is now boiling. We've heated it up from 0 degrees up to 100 degrees. It is now boiling. And we boil it, we heat it up until we can turn it into a vapor. And once we turn it into a vapor, then it is a gas. And we have some labels that we put on these things here. And we say that down here, this is solid. So we would call that ice. Okay, and then right here we have water melting. So I'm going to say melting. And then as it melts, then it's a liquid here. It becomes a liquid. And then once water gets up to 100 degrees, then we start boiling it. And then once it's boiled and it turns into a vapor, we say that it's a gas up here. So we'll say vapor. Vapor, or for water, we have a fancy term for it. We call it steam. We have these different words for water depending on what state it's in. It's ice, it's water, or it's steam. Those are just different words that we use for water depending on, or H2O, depending on the state of matter that it's in. All right. Now, as we pull these water molecules apart from each other, we have some special considerations, and that is enthalpy of fusion and enthalpy of vaporization. And so what's going on there? Our enthalpy of fusion, this is where we're actually taking our solid water and we're turning it into a liquid. And so we would say that our enthalpy of fusion, FUS, so delta H subscript FUS, is equal to some number. There's some standard for this. And the standard for this is 333 joules per gram. 333 joules per gram. And notice there's no degrees Celsius here. There's no temperature. And that's because as we're going from a solid here to a liquid here, we're not changing the temperature. The temperature stays the same. And then when we heat up water, that is our specific heat. So C sub S of water is 4.184 joules per gram degrees Celsius. And here we have degrees Celsius, and that's because our temperature is changing as we're heating it up. And then as we're boiling here, we have our enthalpy of vaporization. And our enthalpy of vaporization is equal to 2,260 joules per gram. And again, there's no degrees Celsius there because we have no temperature change as we're going here. There's no temperature change. And then lastly, we have water as a vapor. And our specific heat of water as a vapor, C sub S of water as a vapor, is 1.89 joules per gram degree Celsius. Specific heat of water as a vapor. Okay, now this is what we call a heating curve. It's kind of like an energy diagram showing how much energy it takes to go to these different phases. And I'll give you an example of how this works in everyday life. Now, husbands and wives will argue over the dumbest things. And the wife and I, this was a few years ago, we were in the kitchen and we were both cooking. And we were cooking something really simple, noodles. It's like, how could you argue about boiling noodles? Well, let me explain. So, the wife takes a pot with some water in it, she puts it on the stove, turns the flame up, and she gets it up to a nice rapid boil. Then she throws the noodles in. And I walk by and I see these noodles boiling in this rapid boil here in the flame. And in my mind, I'm thinking, whoa, that's way too much fire. That's wasting energy here. So I go and I turn it down. Okay, and I feel my job here is finished, right? So I step away from the stove. My wife comes back and she's like, huh, okay, and she turns it back up. And then I walk back and I see that the water is rapidly boiling. And of course, this is not acceptable. And so I go and I turn it down. And of course, that's science. Ah, yes, okay. And so I turn it back down. And she's asking, well, what? She's like, okay, what are you doing? Why are you interfering with the boiling of the noodles? And I explain, well, you're wasting energy. And she says, well, no, it'll cook faster if I have more heat applied to the boiling water. And, so she turns it up. And I say, no, it will not cook faster if you add more heat to it. You're just wasting energy. And I turn it down, right? And up and down, and up and down. It goes back and forth until finally she's like, okay, stop. No, your logic is flawed. And I'm like, whoa, okay, hold on, time out here. Let me explain to you thermodynamics. And she's like, whoa, okay, hold your horses there, Professor Locken. I'm the one who has a degree in chemistry, my wife. She actually has a bachelor's degree in chemistry. My bachelor's degree is in biology. And so she's like, okay, let me explain thermodynamics to you. All right, so we're going back and forth. And I say, okay, so I pull out a paper towel and I grab a marker and I draw my heating curve. And I show her water heating up to 100 degrees. It's boiling. You apply more heat to it, it does not change the temperature. Do you see that? It doesn't matter if it's a slow boil or a fast boil, you do not change the temperature. So turning up the heat, according to laws of thermodynamics, does not change the temperature of the water. You're adding more heat, but you're not changing the temperature of the water. Ergo, the noodles aren't going to cook any faster. And I, drop the mic. And the wife says, yes, but they will not stick together if the water is boiling rapidly. And I'm like, okay, all right, now we're changing the argument here. But to the laws of thermodynamics, anyway, to the laws of thermodynamics, increasing the heat here, as long as it's the same phase, is not going to change the temperature. Okay, so practical application of this. Ice cream. Everybody loves some ice cream. So if you've got some ice cream and you melt your ice cream, and it says here what quantity of energy as heat is required to melt 250 grams of ice cream at 0 degrees Celsius and heat the water to steam at 100 degrees Celsius. So we have ice cream at 0 degrees Celsius as a solid. So that's here. So we're going to start here. And then we are going to have to melt it, which takes us to here. Okay, so we'll end up here. And then we're going to have to heat it up to 100 degrees. And so we're going to end up here, like that. So from there, and then it says, then we're going to take it and turn it into steam. So then we'll end up over here, like that. And that is where we end. So we're going to start here, and then we're going to end here. Now that means we have 3 different legs, 3 different calculations that need to be made. We're going to have an enthalpy 1 here, enthalpy 1. We're going to have another one here, 2, and then a third one up here, 3. Okay? So we're going to have 3 different enthalpies. And when we add them all together, that should give us the total amount of energy. So what I'm going to do is I'm going to start out with my Q1. And my Q1 here, this is going to be melting ice. I'm going to say melting ice. Melting ice. And we have an equation for this. We have mass times C sub S times delta T. And our mass is 250 grams. Our specific heat here is our enthalpy of fusion. So that's 333 joules per gram. And we don't have degrees Celsius here because the temperature doesn't change. And then our change in temperature, there is no change in temperature, is there? It stays the same. And so we end up not using our change in temperature. The temperature doesn't change. Don't put a 0 in there, because if you put a 0 in there, then there's no energy. Okay. Then our second enthalpy. This is going to be to raise the temperature of the water from 0 to 100 degrees. So we're going to go from 0 degrees Celsius to 100 degrees Celsius. And it's going to be our same equation. We'll do 250 grams. Our specific heat of water is 4.184 joules per gram degrees Celsius. Right, that's right here. 4.184 joules per gram degree Celsius times our change in temperature. And our change in temperature, we're going from 0 to 100, so that will be 100 degrees. And then our last one, this is going to be boiling our ice cream. We're going to go from liquid to a vapor. Same equation. We have 250 grams. Our specific heat, in this case, that's going to be our enthalpy of vaporization, is 2,260 joules per gram, and there's no temperature change. No temperature change. Okay, so this is, I should say, to evaporate water. To evaporate our water. All right, so then I do some math, and when I do some math, I'll get some numbers here, And let's see, I ended up here with, I think it was 8.3250 times 10 to the fourth joules. And in this one, I have 1.046 times 10 to the fifth joules. And down here, I've got 5.65 times 10 to the fifth joules. And if I add all of these together, that should be the total amount of energy it takes to melt this ice cream and turn it into steam. And I ended up with 7.53 times 10 to the fifth joules. Okay. So any questions on that? Melting ice cream? Okay. Yes. Is there a specific heat for ice as well? Yeah, that's a great question. Yes, there is a specific heat for ice. There is. I don't think I wrote that down, but that is a thing. There is a specific heat for ice. Yeah, great point. So the question is, you're assuming that ice cream is mostly made out of water, right? And there is some fat and there is some sugar in there. That is true. That is true. And so I just made the assumption that it's mostly water. But yes, you are correct. Yeah, more a snow cone sort of thing. Yeah, maybe I should change this. It's more about snow cone. Yeah, because you are correct. Does it make sense? Yeah, you just can't save it for later. It's not how thermodynamics works. Okay, now, I'm sure you've been asking yourself, okay, so we've been talking about thermodynamics now for a couple of lectures. How do I figure out how much energy there is in my Krispy Kreme donut? Because I love me a Krispy Kreme donut. How do I figure out how much energy is in there, right? I'm glad you asked. That's a great question. So the way that this gets calculated is using something called a bomb calorimeter. Now, the last time we got together, we had a styrofoam cup calorimeter. That's really easy. It's like a styrofoam coffee cup. A bomb calorimeter is a steel container, and inside of that steel container, it's filled up with water, and then inside of the water, you can see there's a reaction vessel. And in that reaction vessel is where you put your Krispy Kreme donut, and then you pump some oxygen in there, and you can see some wires going in there. So then you run some current through the wires, causes a spark. Your Krispy Kreme donut ignites and burns. And it releases that energy, that heat energy, into the water. And it allows you then, you can measure the change in temperature of the water. From the change in temperature in water, you can make some calculations. All right, now the reason this is called a bomb calorimeter is because if you do it wrong, it's like a hand grenade, right? Because you're doing an explosion. You're blowing something up inside of a sealed container. It's bomb calorimetry. They use this in P-Chem. So if you stick with chemistry, they actually do this. And I should have grabbed one of these bomb calorimeters. They're really heavy because it's like really thick steel. All right, so that's how they would figure out how much energy there is in a Krispy Kreme donut. All right, so this bomb calorimeter, it's just a constant volume device that you burn stuff in, and then you measure the amount of heat's given off. So we're going to do a reaction here where we figure out how much energy there is, for example, in a gram of Krispy Kreme donut. So we're going to have ourselves a bomb calorimeter, and the first thing we're going to do is we're going to figure out how much energy it takes to heat up that bomb calorimeter. So this is our heat capacity. The heat capacity is the amount of energy it takes to heat up the whole object. So we have that equation where our enthalpy is equal to C sub S, or times delta T. Now we don't have mass in this one, and this should actually be Cp. We don't have mass in here because we're talking about the heat capacity, not the specific heat. The heat capacity is the amount of energy it takes to raise the whole object by 1 degree. So mass really isn't relevant here. We're going to heat the whole object. by some amount of temperature. And it tells us that the energy released here is 26.38 kilojoules. And that's equal to the heat capacity times the change in temperature. And our change in temperature is 27.20 degrees Celsius minus 23.40 degrees Celsius. And so when we do the math on this, we're just solving for CP here. So our heat capacity is going to be equal to 6.94 kilojoules per degree Celsius. So that's how much energy it takes to heat up this bomb calorimeter by 1 degree, or to cool it down by 1 degree. So then we go and we grab ourselves some Krispy Kremes. And so the question here is, you've got 10 grams of Krispy Kreme. You get yourself 10 grams of Krispy Kreme donut, and you want to figure out how much energy is there per gram of Krispy Kreme donut. And so we have this same equation where we have our energy is equal to our heat capacity times our change in temperature. And we're trying to figure out how much energy there is. So we're going to say our Q here is equal to our heat capacity, which we just calculated here. That's going to be a negative 6.94 kilojoules per degree Celsius. Okay. And it tells us here that we heat up our bomb calorimeter by 23 degrees, so 23.2 degrees Celsius. So when we're done, that tells us that we released 161 kilojoules of energy. You're like, okay, that's nice. That's how much energy gets released when we burn that 10 grams of Krispy Kreme. But how much energy is there in 1 gram of Krispy Kreme? Well, we'll just take this, divide it by 10 grams, and that gives us here 16.1 kilojoules per gram is the amount of energy in a Krispy Kreme. So that would be released there. Amount of energy in 1 gram of Krispy Kreme donuts. Have you ever had a Krispy Kreme donut? Few people have. Man, they are tasty. I love me a Krispy Kreme donut. That's all fine and good, except in the United States, we're just kind of weird in that we don't use joules to measure heat. We don't use joules to measure energy in our food. We use calories. The rest of the world uses joules. So in the United States, we measure energy in food in calories. But to make it even more complicated, we have normal calories, and then we have what we call kilocalories. We have calories with a big C and calories with a little c. Yes, because we're weird like this. And so when people come to the United States and they're like, oh, how many joules are there in your food? And you're like, joules? I don't know what the heck a joule is. I'd never heard of that. Did they put joules in the food? You call the cook. Cook, did you put joules in the food? And the cook says, I've never heard of joules. And so you tell the foreigner, no, there's no joules in the food. And they're like, woohoo, this is all diet food, right? I can eat as much as I want. Yeah, but there's plenty of calories, aren't there? Yes, America is weird like this. Now, the conversion from calories to joules is 1 kilocalorie, or 1 big C calorie is 4.184 kilojoules. And you look at that number and you go, oh, that looks familiar. Yes, it does look familiar. That's the amount of energy it takes to raise 1 gram of water by 1 degree Celsius. And so in the United States, we say that the energy that it takes to raise 1 gram of water by 1 degree Celsius is a calorie. The rest of the world says that's 4.184 joules. Because, we're weird like that. Now, at some point, maybe we'll get together and we'll work things out. But I'm not holding my breath. All right, so that's the difference between joules and calories, yes. I don't know if, I just saw this on the news. There was some college student who was road tripping down to Iowa to get Krispy Kremes. Maybe you saw this. We used to have Krispy Kreme stores in Minnesota, but I guess they stopped for whatever reason. and people still like Krispy Kremes. So this college student would drive down to Iowa, load his trunk up with Krispy Kremes, then drive back to Minnesota, sell them, and make money off of this. It's like an 8-hour road trip, and he's like making lots of money off of this. And Krispy Kreme found out about this and stopped him and said, no, we're not going to let you do this anymore. And I'm just dumbfounded. Like if somebody came into my store and said, I want to buy 100 boxes of your product, why on earth would I say no? I'd be like, here, have an extra one for free, right? So Krispy Kreme banned him from doing this, and then this blew up all over social media. And then Krispy Kreme was like, okay, now everybody hates us, so here, kid, come back. We'll give you a bunch of free Krispy Kreme donuts. So the kid is now making the road trips again and selling their Krispy Kremes. What a way to pay for school, right? Found his own little niche. Okay.